Welcome to my panel talk at the Undergraduate Architecture Mentoring Workshop at ISCA 2021. I'm going to spend some minutes to talk about what I think about applying to grad school and doing impactful research. And I was asked some questions, and I will follow that structure. I was asked to introduce myself and the research group and the research we're doing first, so I will start with that one. Hopefully, you will enjoy what comes next. So let's start with introduction and my research group. I'm a professor at ETH Zurich in the Information Technology and Electrical Engineering department and Computer Science departments. The ETH department is more like an ECE department. And I've been here for almost 6 years now. Before this, I was at Carnegie Mellon University. I was there for about 7 years. And my last PhD student at Carnegie Mellon is going to graduate very soon, this summer actually. And I'm still affiliated with there. I got my PhD from UT Austin. And then I started the computer architecture group in Microsoft Research Redmond. And I worked at multiple companies, both during and after my PhD, Intel and AMD. I did a bunch of internships at Intel and AMD during my PhD. And I worked at Google, VMware, and I consult with several companies today. You can find more information about me on my website. But the best way to reach me is via email. But don't be discouraged if you don't get a response. I get a lot of emails, so feel free to resend. And you can learn more about our research in what comes next, and you can always visit our websites, as you can see over here. So I do research and teaching in computer architecture. That's what I'm really excited about. We work on computer systems, hardware security, and bioinformatics. I'm actually interested in all aspects of computer architecture. We do a lot of work on memory and storage, hardware security, fault tolerance, hardware software cooperation architectures for bioinformatics, health, and medicine. But I'm actually excited about all aspects. And what I'm really interested in is to build fundamentally better architectures, both at the small scale, each component and interactions between components, as well as a larger scale that connects these components. And you can see these are the research topics that are listed on top. We're very interested in hardware, software, cooperation, and all aspects over here. These are 4 key current directions that my research group is following. How do we build fundamentally secure, reliable, and safe architectures, fundamentally energy efficient and high performance architectures, more memory-centric architectures, low latency and predictable architectures, and architectures for genomics, medicine, health, and machine learning, as well as how to use machine learning for architectural design. I'm going to go into these very high level by flashing a lot of slides later on. But I'm a believer that the older thinking about computer architecture has a narrow view. I don't think of computer architecture as just about the hardware software interface and the lower level implementation of that interface, which is microarchitecture. We take a much broader view where we co-design across the hierarchy all the way from algorithms to devices. So it's really software plus algorithms, and the hardware all the way into the devices, circuits, etc. are within the domain of what we look at. Of course, our core is at the architecture in my research group. So this is motivated by the axiom that we would like this sort of expanded view, algorithm to devices, to achieve the highest efficiency and performance, as well as other metrics like reliability, security, fault tolerance, dependability, robustness, etc. That's why we believe that this is a good approach, and I think this is being validated by many things that are going on in industry as well as research right now also. So we would like to co-design across the hierarchy, algorithms to devices, and specialize as much as possible within the design goals that are set by us or by others. This is a very busy slide that goes into a lot of research that's going on in the group right now, which is under the umbrella of building fundamentally better architectures. I'm not going to go into the details of it a lot. You can take a look at it. You can also watch our online lectures that talk about a bunch of these. But there's a lot that goes on in my group. It's a large group. I'm going to introduce it in a little bit. And I'm excited about everything essentially over here. And let me jump into the group. You can find a lot of information on our website also, safari.ethz.ch. This is the group motto designed by my students over here. It's called the Safari Research Group, and there's a story behind it, which we don't really have time to talk about over here. And this is a picture of the group pre-pandemic. You can find people online also. Also, you can find our newsletter, which was our first newsletter in April 2020. And this was the picture that was taken before the pandemic started. This is a picture after or during the pandemic, let's say, during our Christmas and New Year's or end of year meeting or celebration, let's say. And you can find more information about our research in this more recent newsletter from January 2021. If you're interested in my students and what they're doing after they graduated, you can find information about them also. In total, we have about 16 graduates right now for PhD and a number of graduates in postdoc, and they go to both industry and academia, as you can find out online over here. I'm a big believer in teaching and research going together. I think teaching drives research and research drives teaching, and we should look at these things in conjunction. And I believe these are two sides of the same coin in the end. In research, you educate the entire world about something that no one knew. In teaching, you educate, hopefully, in the entire world about something maybe everyone knew, right? And I think I use this principle in my research. I'm going to talk a lot about principles later on in answering some of the panel questions. We focus a lot on learning and scholarship. I think these are the most important things. In the end, nothing else matters that much. So we focus on insight, learning, and scholarship. And I encourage a lot of new ideas. So if you have new ideas, feel free to contact me. And I think we strongly believe that the quality of work defines your impact in the end. And I would encourage everyone to think about this. If you have good mindset, good goals, and good focus, hopefully you can make a good impact on the world. And I assume people who are attending this workshop are excited about this because this is the undergraduate research mentoring workshop. And hopefully this talk will give you some perspective, my perspective on this. Okay, we do a lot of research and teaching, and you can find a lot of it online. We have a YouTube channel. Actually, we have multiple YouTube channels at Carnegie Mellon. I had a different YouTube channel. We have a different one right now, and they're combined in some sense. You can find a lot of information about our research online, as you can see, as well as our teaching. These are the latest edition of the major courses that we deliver. This is the Bachelor's Computer Architecture and Digital Design course. That is a second semester course. And this semester, it just ended actually last week. And we live streamed the lectures. It was an interesting experience and hopefully useful. You can find the entire lecture set on YouTube. This is a 500 plus student course in the bachelor's, and we also have a more advanced computer architecture course which you can find also online. And there are also other courses that we have online that I didn't put over here. Many seminar courses and also project and seminar courses where students do hands-on projects. And you can find the public, essentially all lectures of these major courses online on this website. And this is a more detailed view for digital design and computer architecture. We're going to make these slides available so you can find these online as well. And this is the detailed view of the computer architecture course. Okay, and if you're interested in more information, you can always find interviews on our channel on research and education that I have delivered in the past, as well as more thoughts and suggestions based on the speeches that we have given. This talk is actually based a little bit on the how to build an impactful research group talk in the panel that I delivered in the panel at DAC, a Digital Design Automation Conference last year. And if you're interested in any of the papers, etc., we do a lot of things open source, and you can find them online, including all teaching materials as well as almost all research materials. So let me give you a quick overview of the example research topics we follow, because in the end, your goal is to do a PhD, and I think it's really important to be excited about what you're going to work on into the future. I'm going to give you my perspective on what we're following very quickly. Hopefully there will be a lot of slides, but I'm going to try to go through this very quickly so that I can give you answers to some of the other panel questions. As I said, we want to build fundamentally better computer architectures, and we're focusing on these 4 different directions: fundamentally secure, reliable, and safe architectures, fundamentally energy efficient and high performance, more memory-centric architectures, low latency and predictable architectures, and architectures for AI, ML, genomics, medicine, health, as well as using some principles from these other fields in computer architecture and computing systems. So I'm going to give you some sampling of the research over here. Clearly, there's a lot that goes on in a large group like mine. I'm going to give you just a sampling. I'm not going to be able to talk about everything that we do clearly, but this should not be taken as I'm not interested in many things. I'm actually interested in almost everything. And I'm a big believer in listening to other people's ideas and amplifying them. So I like thinking about new ideas in general. So I think a huge challenge and opportunity we have for our future is building high performance systems, even higher performance than what we have today, because we have a lot of tough problems facing us, and we want to solve all of those tough problems. At the same time, we want security, personalization, and privacy in all aspects of our lives, especially important in health, medicine,
spaces, device, and robotics, for example. We want personalization, privacy, and security in all of these systems. Self-driving car, for example, or medical architectures like genomics architectures. So I'm very excited about genomics. We do a lot of work in this topic starting from 2007 or so. And this is a recent paper that we have written on accelerating genome analysis. I'm not going to go through the details of it, but there are a lot of opportunities here in hardware, software co-design, algorithm architecture, device co-design. This is a paper that we presented at Micro last year on accelerating approximate string matching, for example. There are a lot of exciting new genome sequencing technologies that are happening, that are coming up. This is Oxford nanopore technology, for example. We do a lot of work on this topic. And the future is going to be actually very, very edge and low power and mobile, as you can see over here. These are real technologies where you can sequence genomes and attach to your cell phone. But we're lacking the computational power. That's why we want to accelerate it, make it quick. And the fundamental question that we're trying to answer is, can we actually do the sequencing and analysis, complicated analysis, within real time? Like, let's say within a minute or within seconds, if possible. Within several minutes, let's say, so that a doctor in a critical situation can quickly prescribe some drug that is personalized to the person and that can actually be effective. So if you're interested in this, there's a lot more to learn, and I have a lot more to learn also. So we're doing some research, and you can find out about it in this lecture that I've given recently. Also some other lectures that we cover in some of our computer architecture classes, as well as some project courses, as you can see. Okay, so the problem in these applications, like genomics application and many other applications, is computation is actually bottlenecked by data today. And we have a huge bottleneck in data storage and movement. Essentially, modern systems, modern computing systems are bottlenecked by memory. And we're tackling this challenge in many, many different aspects today. And this is an early overview paper that we have written and presented in the International Memory Workshop, which you might be interested in taking a look in 2013. And after that, we did a lot of work on understanding different aspects of memory. And security, reliability, and safety is one example of it. We're actually looking at security, reliability, and safety beyond memory also, but memory is a big component of this. So we built a lot of infrastructures to understand memory systems, scaling issues, security issues, latency issues, performance issues. And these are some FPGA infrastructures that we built in my group, and you can take a look at them in the papers that are referenced over here. This is where RowHammer was actually analyzed significantly. And we actually open source a lot of our infrastructure, SoftMC infrastructure being one of them, and other folks in both academia and industry use them. And you can also find these online. But these infrastructures enable a lot of research, actually. For example, one research that the infrastructure is enabled is the RowHammer research that is quite famous right now, and you might be actually have learned about it. This is the fact that you can predictably induce errors in most DRAM memory chips. And essentially, this is a simple hardware failure mechanism that can create a widespread system security vulnerability. And people are writing interesting articles that look like this. Forget software, and our hackers are exploiting physics. So I'm not going to go into the details of RowHammer, but after we wrote our initial paper in ISCA 2014, Google showed that this bit flips that you can induce reliably can actually be used to take over a system completely in this Project Zero article. We have mentioned this in our paper, but we didn't show a working prototype. So later work actually showed many working prototypes. And this work is quite interesting, I think, as a big security and safety and reliability problem in the main memory technologies that are dominant in our lives. And if you're interested, you can take a look at the papers. Certainly, there are a lot of papers that we have written. This is more of a retrospective invited paper in topics in hardware and embedded security that appeared in TCAT. But after that, there has been a lot of other research in 2020 that showed that RowHammer did not go away. It's actually becoming worse. And the manufacturer's solutions are actually not sufficient because you can circumvent them. So RowHammer is still an open problem. And security by obscurity is likely not a good solution. And we actually have a DRAM security workshop at this ISCA talking about RowHammer and related memory security and safety issues. And there are other works that you can find. Of course, we, as well as other people in the research community, are looking at solutions. And this is a very fruitful area of research. And if you're interested in even more, you can look at more detailed lectures on RowHammer in our architecture classes, as well as some special lectures that we deliver in different venues that are also online in our YouTube channel. We're also looking at flash memory and SSD storage, essentially reliability, as well as performance. We're also looking at emerging technologies like phase change memory. I don't have slides for them over here, but you can find it in our courses. And we build infrastructures for these memories, especially flash memory as well. So one important takeaway in all of this research is you want intelligent controllers to actually not run into these security, safety, reliability issues or correct them when they happen. And this brings me to my next challenge. Can we make memory more intelligent going into the future? Why do we want that? Because we want high performance, energy efficiency, and sustainability at the same time. But we also know that we have a big problem. Processing of data is performed far away from the data. We have the memory computing dichotomy today. As a result, data moves a lot in our systems, and that's not very efficient because a memory access is orders of magnitude more costly in terms of energy as well as latency compared to, for example, an addition or a multiplication or a floating point multiplication addition operation that you do in a processor. And we did this work with Google in 2018, which was published in ASPLOS, where we showed that more than 60% of the total system energy is spent on data movement, for example. And we want to change that, basically. This happens because our current design principles are very processor-centric. There's a huge dichotomy between processing and memory is not an active component. As a result, we have great energy waste and great performance loss because we're moving data all around and we're designing systems that are complicated. Okay, so basically we're trying to enable a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, and make computing architectures much more data-centric. So I think of this as computing architectures with minimal data movement, and I think there's a huge opportunity to impact the future. And I also think of these as enabling fundamentally energy-efficient architectures because data doesn't move. These are more data-centric architectures. I also think of these as fundamentally higher performance architectures, again, data-centric architectures, because data gets processed right where it resides or where it's produced, essentially. So there are many, many questions to answer over here. Essentially, how do you offload tasks to memory? How does memory become an active component? What applications can benefit? How do we redesign the algorithms to take advantage of it? How do you design the memory? How do you design the processor core? How do you design the interfaces? How do you design the hardware and the software, system software compilers and languages, algorithms? And how do we think about theoretical foundations of computing? Because computing has been very processor-centric, even in its core theory so far. So we're trying to change all of this. Of course, we're trying to do it step by step. And we're thinking of memory as a conventional accelerator to begin with, but this may actually change going into the future. But it's very different from other accelerators that we're designing because it's on the other side of the memory bus, as you can see in this picture. So this is an old idea. Processing in memory is not a new idea. It was first explored in 1960s. Earlier in analog computers, maybe you can think of them as doing processing close to memory as well. But we're thinking of it from a different perspective. And there are two approaches to it. Processing using memory by exploiting the analog computational principles, operational principles of memory to do computation. And processing near memory by putting logic near to memory as opposed to having logic far away from memory. And I'm not going to go through the details of it, but I'm going to flash some papers that we have written on this topic. I'd recommend, if you're interested, looking at this modern primer on processing in memory, because this is a state-of-the-art survey and overview that talks about the newer reasons for processing in memory, as well as talks about the history a little bit, not a lot, and talks about some open issues. And we've also written some other review and open problems articles you can see. And we also have research articles over here that you can find and read online, including very recent ones, for example, that looks at analog operational principles of memory and how to actually expose them to create more powerful primitives. And we have also some relatively old research that talks about specialized acceleration mechanisms as well as more general purpose acceleration mechanisms like the work we did with Google, as you can see over here. I'm also excited about using processing in memory for security purposes because you need a security infrastructure on the memory side also. And we do research on understanding modern devices to generate physical unclonable functions as well as random numbers. And we actually have a paper coming up at ISCA that's not on these slides called QUAC TRNG that introduces the idea of quadruple row activation in real DRAM devices. So of course, this is a paradigm changing idea, processing in memory. How to enable adoption of processing in memory is important, and that is also what we're doing. I'm not going to go through this. I'm going to refer you to some other works over here, but we do need to revisit the entire stack in the end, but we can get there step by step by keeping adoption in mind. So one of the things that I'm excited about is this work that is happening with UpMem startup that is in France. These folks have built real processing in memory chips where they actually have a processor next to each DRAM bank. And they have real DIMMs, as you can see. We have access to these DIMMs, and this is an example picture from a paper that we have online you can find. And you can find more information about our analysis of this real processing in memory chip. So this is happening, basically, and I believe there's more to come. And Samsung has recently announced that they are also looking into processing in memory. In fact, they have a paper at ISCA in the first session that talks about their processing in memory architecture. from an architectural perspective. They had a paper at ISCA as well. Okay, if you're interested in the experimental analysis of this UpMem PIM engine, you can find it on our website in an archive. And we also look at methodology and workflows to actually enable processing in memory, and you can find other papers on our archive. And you can also find many detailed lectures on PIM, processing in memory, as you can see on our advanced architecture course. And if you're interested in a more detailed treatment of processing in memory and memory-centric computing systems, you can also have resources like this that I delivered at IEDM conference last December. This is a tutorial that's about 2 hours if you're interested in this. Okay, I actually believe that processing near data, processing in memory, can enable new medical platforms like what we are envisioning with genomics. I'm not going to go through this, but some of these papers talk about these issues. We do need to have processing near data to actually have low latency, low energy analysis of genomes, for example. And if you're interested, again, I'm going to flash these slides that you can take a look at. So finally, I will mention a few things about fundamental low latency computing architectures. That's another direction that we're tackling. I'm not going to talk about all the other directions, of course. And I think this low latency is important because we really want to truly reduce memory latency at the source of the latency, which is memory itself. And we have some works in this area, as you can see. I'm going to flash these, and there are a lot of interesting ideas over here. And this is most recent work in ISCA that essentially provides capacity latency reconfigurability in DRAM. We also look at SSDs, solid state drives, as well as phase change memory for reducing latency, but I don't have time to talk about any of these. Instead, I will refer you to low latency memory lectures that we deliver in our classes. And you can also find a lot of other lectures on individual research topics on our websites and YouTube channel. Okay, basically, I think all of these ideas are very, very interesting. And I think what excites me in research is to revisiting the entire stack so that we can enable fundamentally better computing systems. But we would like to also keep the adoption issues in mind. We can get there step by step in the end. And ideally, we would like to see each step nicely. Okay, we do a lot of open source artifacts, as I mentioned earlier. You can find it on our GitHub. And this is a snapshot that I recently pictured. You can see that we also work on bioinformatics quite a bit. We have some modeling infrastructure for COVID-19, for example. We look at privacy issues in bioinformatics. And this sneaky snake is our recent algorithm that accelerates pre-alignment filtering. And clearly, we have a lot of other work on memory simulation, etc., which you can find online. These are some old slides that have some links here. And you can find a lot more. And I strongly believe in this open sharing of infrastructure, as well as open sharing of data and results, as well as teaching. I think that's really important for the entire world going into the future. Okay, so let me now tackle other panel questions. I've tackled the question on who am I, who is my group, and what kind of research we're doing. There are some other panel questions that are also important, and I think that's going to be the basis of discussion in the panel. And this was one question. What is the grad application process at your institution? What do you require? So right now I'm at ETH Zurich, so I'm going to answer it from a perspective of an ETH Zurich professor. Carnegie Mellon has a completely different application process. I'm happy to contrast it very briefly here, and I'm happy to take any questions during the Q&A session also, or the panel session. So at ETH Zurich, PhD starts after a master's degree. And I believe this is true for most of Europe, almost all of Europe actually. Except for a few exceptions, you need to have a master's degree to apply. Now we have a direct PhD program as well, but that's a very limited set of pilot program at this point, and it's not exactly the same thing as a direct PhD that you do at Carnegie Mellon, for example. And I'm happy to talk about that separately when the time comes for the panel. So you can apply for a master's degree first if you're a bachelor's student. Of course, if you already have a master's degree, you have no problem. I'm going to talk about that. But if you are a bachelor's student, you apply for a master's degree first. And then, of course, you may decide to go for a PhD. And if you're already at ETH Zurich for a master's, it's easy. Now, if you're outside ETH Zurich and if you already have a master's, that's also easy, in my opinion. Of course, you need to satisfy the admission criteria, right? So master's admissions after bachelor's are centralized and handled by the departments, and each department handles it separately. And I'm happy to talk about that. Master's admissions are more of a master's admissions, not a PhD admission process. What I'm going to talk about later is the PhD admission process. PhD admissions are decentralized and handled by the professor. So professor has a lot of say, and the ETH Zurich doctoral office checks the eligibility but usually that eligibility check is satisfied if you have a master's degree. Okay, so let's talk about the application process for a PhD for Safari. So we actually have a common website. Safari is my research group, as I said. We actually have a common website that everyone can apply, not just PhDs, but postdocs, internship, visiting researcher, or any kind of research that you would like to do with us, including remote research. We have the same website, and anyone who comes to Safari from outside of ETH is required to apply through this, and you can find what we ask for over here. I'm going to briefly mention that as well. And I think the process that we follow is usually, if you do an internship with the group, this is very useful and desirable, and it's very much recommended. You can do this during your bachelor's and master's degrees or at any other time. And that internship is actually very useful for us to see how we work together and then decide whether we want to go for a PhD afterwards together, right? And I think apart from this, familiarity with the research area and passion for research is very important for me. Of course, there are some application documents we ask in the previous slide that I showed you in our website, for example. A good personal statement that shows your passion, familiarity, etc. is important. A good critical review of papers is important. We ask for review of papers, a critical review, and we have a methodology for reviewing papers that I recommend everyone to follow. That's important. Good interview with the group and myself. So we do actually interview every candidate carefully, regardless of whatever position they're applying for. That's important. A good mindset, goals, and effort. They're important. I'm going to talk about them. Good communication skills and communicativeness are also quite important. So there are a bunch of things. It's not a perfect process, obviously. And our focus is really on insight and getting to know your mindset, goals, and what kind of characteristics that you have, and what do you want from a PhD, as opposed to essentially looking at numerical figures. Numerical figures are much less important for me, as I will mention soon. Okay, candidate characteristics is going to be an important part. What do you look for in a candidate? What are a few things that stand out to you? And here, I think there are a lot of things actually. A PhD is a growth process, as I will mention in a little bit. And I think a PhD is not for everyone in the end. It's a long road. Commitment and resilience are very critical, and you really want to be committed to do a PhD, because it takes anywhere between 4 to 6 years, sometimes longer, of course, but usually in systems and architecture, in my group, it's somewhere between 5 to 6 years on average, let's say. It doesn't matter what degree you have before. Sometimes if you have a master's degree and you're more mature, you can actually do it relatively more quickly, but doing it lower than 4 years is usually not desirable or possible, actually, because there's a lot to do in systems and architecture, right? So motivation and mindset are extremely important. I also look for creativity. These may be hard to judge. Resilience is extremely important. Hard work, boldness, perseverance, and commitment. I'm saying maybe similar things over here. Intellectual strength is important. Openness to feedback is very important for me. Communicativeness, emotional intelligence is important. And I think execution capability, ability to execute things until the end, from the very beginning to the end. And I think all of these are maybe important in the end. It's hard to put a priority to these things in the end. I mean, maybe the prioritization is motivation and mindset and resilience and commitment. Those are the most important, perhaps. But I think to do a really strong PhD, a good PhD, I think you need a combination of all of these. And you may not have all of them at the beginning, but at least you should have some sort of basics for each of them. And you grow also during a PhD. You learn some of these skills in a much better way. And I think that's the beauty of a PhD as well. Again, how to select students was asked. We try to look at these characteristics based on the statement, the interviews. I think personal interviews are very important. And certainly if you do an internship, that's a very important one. And we have had a lot of interns in my group that have stayed for 6 to 9 months, a year. And they've actually done very interesting research, and they published papers at top venues during their internships. And they later became master's or PhD students with us. Okay, the third question is the easier one, perhaps, GPA and GRE. When looking at applications, how important are GPA and standardized test scores, e.g. GRE, to you? GPA is part of our application process. We ask for it, but it's not really important enough. We don't do any decision or filtering based on GPA in the PhD application process. Now, if you're applying for a master's to ETH Zurich, then people look at GPA, and it bears some importance for sure. What school you come from also bears some importance over there. And I'm happy to talk about that in more detail. But for a PhD in my group, I don't put a lot of importance on GPA, because I really want insight and not numbers, as hopefully it's clear earlier as well. Individual courses that you take can be important, and how you've done, depending on the nature of those courses, of course. Taking our own course, my course is online, for example, and having a similar mindset, developing a research mindset is important. But more than anything else, motivation, what kind of characteristics you have, skills and insight, they're much more important than a GPA, for example. And in the end, GPA is not a predictor of great research anyway, because research skills are different from skills that you need to get a strong GPA. And GPA is affected by a lot of the characteristics of your undergraduate institution and undergraduate mindset, whereas research mindset is different. So we do not require GRE scores. Neither ETH nor I myself require GRE scores in general. Of course, you can supply them. TOEFL and IELTS are required for non-native English speakers, and this is important to a level, of course. But of course, we do verify the English communication skills through your writing as well as through the interviews. Okay, what do you look for in a personal statement? I think I don't have a very detailed answer to this. I try to look for basically all of these characteristics that I mentioned earlier. Motivation and mindset, creativity, resilience, hard work, boldness, perseverance, commitment, intellectual strength, openness to feedback, communicativeness, emotional intelligence, and an indication of ability to execute things until the end. And of course, there's no way of writing a statement that satisfies all of this, actually, clearly. And there's no one single way of writing a statement as well. So in the end, you got to be yourself, and you got to figure out what you want to do during a PhD and convey it in the best way, in a personalized manner to yourself. But of course, if you can convey how you satisfy some of these things with examples potentially, that helps. But again, statement, a good statement, of course, potentially gets you to be interviewed, but interview is also important afterwards. Okay, now let me talk about some things that I think about as important for doing high impact and good research and going into a PhD as well. Hopefully these will be useful for you. I'm going to borrow a lot of slides that I used for the Design Automation Conference workshop. I think a PhD is really about continuous growth. It's about learning and independence. It's about learning how to be independent also. In the end, you always increase the bar. If you have the mentality that you would like to always increase the bar when you reach a bar, that's a good mindset for a PhD, basically. You really want to grow all the time, learn, become more scholarly all the time, become more independent so that you can tackle any research problem or maybe any problem in the end. So this is the way I view a PhD in the end. So in the end, how you succeed is dependent on how good you are in, or how good you can be, how quickly you can learn to be, to grow basically. And in the end, there's no one single way of doing a PhD. All of my PhD students, in my opinion, have taken different paths, if you will. So you need to have personalized methods. I need to be a good learner to figure out how to actually navigate the unknown, if you will. So you really need to find the methods that work for you, in my opinion, in doing a PhD and in going for a PhD as well. So doing so requires many characteristics which one can learn, but you need to start with a good basis of many characteristics. So motivation and mindset are therefore extremely important, and commitment to actually do this, resilience, are extremely important. So that's why I rate them very highly. So let me talk a little bit about motivation and mindset, and I talk about this with my students. I think it's very important to start out with the right motivation and mindset, with a good motivation, good goals, as opposed to the wrong goals, let's say. Because this really sets the culture of the group and your goals of the group as well as yourself. So I think a big mindset we have in my group is to change the world positively, have high influence, be scholarly, etc. And a second mindset that we have, especially it's very important for me, is to enable the students to achieve a potential that they did not even think that they could ever achieve. And hopefully at the end of the PhD, they would say, wow, I did achieve this, and I never thought I would have achieved this. So if this is successful, if both of these are successful, then I would call it a successful PhD. Of course, changing the world may not happen until after the PhD, right? But second one is very important to me. So it's really not publishing papers. Papers are potentially a byproduct so that you can actually show to the world new ideas so that you can educate the community, right? But the goal is not publishing papers. The goal is not fame. The goal is not money. The goal is not really any quantitative measure, really. these two, mindset 1 and mindset 2, cannot be measured quantitatively as far as I am concerned at this point. So it's really important to have the right motivation and mindset. So, and in the end, motivation correction may be needed at times during a PhD. So it's important to be ready for this. It's important to be ready for feedback and change during a PhD and even after a PhD, basically. So that's why it's important. And my personal principle is to build a team of excellence by getting motivated students that have a good mindset and good motivation, and having a team of excellence. So the second thing that follows from this, I believe, is focusing on learning and scholarship. I think these are extremely important. The focus should really not be on quantitative measures. It should be on learning and scholarship on an individual basis and on a collective basis as a group, as well as a community. And I think we need to do more of this in our community. Let's not focus on quantitative measures like paper counts, citation counts, etc. Those are really not important. I know people try to do that, and it's not great, unfortunately. It's really about learning and scholarship in the end. So for this, I think it's really important to create an environment of freedom. And I try to do this in my group, create an environment that values free exploration. I think that's very important. Openness about everything, collaboration, hard work, and creativity. I mean, you can add more things over here, but these are the 5 things that I chose to put on the slide because I think free exploration is really important, and open communication. So in my group, there are no boundaries. Everybody can collaborate with everybody on any project. They can help each other in many projects, and certainly they can, as you can see, you can also see this in the papers, right? In papers, there are many co-authors because a lot of people collaborate with each other openly, and we value these characteristics. Okay, what is the goal of research? I think that's also important. We would like to generate new insight in the end that can enable what previously did not exist, right? And essentially, research is a hunt for insight that can eventually impact the world. So that's why we focus a lot on insight. I encourage new ideas. I encourage people to bring about those new ideas openly in any meeting. So I'm actually, I love actually hearing about new ideas, and I like being a sounding board for these new ideas because I think new ideas are really what enables progress, and that enables new insight as well. So this is one slide from one of my courses, actually several of my courses. You can find one example presentation over here. But this is some basic advice for good research. I'm going to go through this relatively quickly because I think this could be useful for undergraduates who want to do research going into the future. I would recommend choosing great problems to solve. Having great taste is important, and developing that great taste is also important during a PhD. A good problem is difficult, important, and potentially high impact. If not immediately high impact, it's potentially high impact, right? Reading heavily and critically and analyzing critically, doing critical thinking is important. Trying to think big, out of the box, not restraining yourself to tweaks and constraints of today, but thinking about adoption issues to enable your big ideas is important. And this comes partly from thinking critically and focusing on big problems. Aiming high, being rigorous is important, being scholarly is important, and writing and presenting extremely well is important. And I think if I had to summarize things for basic advice for good research, it will be this slide essentially. Well, that's why you have that slide. So there are many principles on the previous slide. I'm going to focus on a couple of them. Setting the bar high is important for yourself as well as for peers around you, but most importantly for yourself to begin with. And this is my principle basically. The goal should be to enable my students to achieve a potential that they did not even think they could ever achieve. And this cannot be possible without setting the bar high, right? If I set the bar low, I will achieve low, and we can call it quits after that, right? But if you set a bar high, maybe you may not be able to achieve the bar, but you will aim really high and you may actually achieve something that nobody thought you would ever achieve. So low bars are easy to achieve, and that they limit our potential in the end. So that's why this is the motto of our group: think big, aim high, enable positive change. So we also reward good positive behavior that helps with this culture. And I would recommend everyone to read Hamming's You and Your Research transcript. There's actually a video of it also, but I'm not sure if the video is consistent with the transcript because it may be a talk that was delivered separately, right? So focusing on fundamentals is important for me. Fundamentals and scholarship are critical in my group and in my research. Hypes come and go, so it's really important to actually focus on fundamentals. And it's good to think about what your research will enable or what kind of impact it will still have 10, 20, 30 years down the road, right? So that's why I think choosing problems is important, and guiding your group and your peers toward them is also important. But of course, I like giving a lot of freedom to my students so that they can explore and they can make the mistakes so that they can learn from the mistakes as well. So this freedom is really important, I think. So I've already mentioned this principle. Teaching and research are two sides of the same coin. And we actually use this principle in my classes as well. So I care about teaching a lot. And teaching and research are all about scholarship in the end. Both long-term and short-term is affected by teaching. And as I said, teaching is teaching to folks that educating folks about something that everybody knows about. Research is educating folks about things that they didn't know about. No one knew about, but except for the people who did the research, right? So research motivates teaching and teaching motivates research. In the end, I actually introduce a lot of ideas, cutting edge topics in my bachelor's course. I didn't put, for example, processing in memory is also here, but I talk about processing in memory, RowHammer, meltdown, Spectre, and key issues in technology scaling in my bachelor's course. And you can take a look at that, as I mentioned earlier. And all courses can have research examples in the end. Okay, another principle is emphasizing clarity and rigor in communication. I think this is really important as an undergraduate applying for a PhD as well, because in the end, this is really important for a high impact. And clarity and communication is really important for both teaching, scholarship, education, research, writing papers, delivering talks, and we have a lot of guides about this in my research group. Collaboration is important, I think, fostering collaboration within the group, across groups, and with companies. And I think this is a good principle for good research as well. So that's why we engage with companies. We engage and collaborate with researchers who fit your mindset. But in general, it's best to collaborate, not fight. I see, unfortunately, the opposite of that sometimes. So it's better to actually enable our community to collaborate as much as possible and foster collaboration in general. So strive for the highest excellence in the end. So reaching out is also important, and I think we have a good heterogeneity in my group. I'm happy to see it. So we actually have a good diversity in my group, and this is partly enabled by reaching out, in my opinion. So we do a lot of reaching out, not just me, but also my other group members, talk about our research. I like listening to everyone, especially my students. And teaching, education, and collaboration is important. So feedback is important. Again, this is an important characteristic for a PhD and as well as undergraduate researcher as well. Receiving and addressing feedback is important, but do not get derailed, because not always feedback you receive, you may receive a lot of feedback, but feedback you receive is not necessarily good, right? So you need to actually filter out the feedback carefully. And working with your advisor is important, I think. Reviewer feedback is an example of this. But you receive feedback in many different ways. So valuing feedback is important, but filtering it down to make it helpful is important as well. So take the feedback positively. They can be helpful, but it's not always right. It could be misguided. It could be incorrect in some cases. They may not really understand what you're trying to do, etc. So do not be derailed. This is very important. I know people who have potentially quit their PhDs or quit an entire field because their feedback they received was not right. For example, Hugh Everett, who did his PhD in theoretical quantum physics in 1957, I believe. He developed the many worlds interpretation of quantum physics, and he had to quit the field or for whatever reason. But the main reason was actually he did not get positive feedback about the many worlds interpretation of quantum physics at the time. The key players in the field in quantum physics at the time were actually quite negative about it. And he was quite discouraged even after he introduced the idea in quantum physics, so he quit. But later, there was empirical evidence that came about in the 1980s, 1990s that showed that this many worlds interpretation actually may be one of the strong interpretations of quantum physics. And today it's considered a respectable theory in addition to other theories in quantum physics. So this is a good example of someone doing their PhD and getting feedback that's not right. And later this feedback was invalidated by the evidence that was gathered empirically after 25 years, let's say. I just made that number up, but 25 to 30 years after they did their PhD. So you should keep feedback in context. That's really important, basically. People may not have the right mindset when they're giving the feedback, and that should not derail you. Let me put it that way. That should make you think about your theory and make it stronger and stronger, but that should not derail you. So you need to apply corrections to it sometimes. So as I said, do not let rejection or negative feedback derail you. Be ready for it, in fact, because this happens in many, many areas. And encourage your students, actually. I try to remind and encourage my students whenever they get a rejection. There are works that were rejected once, twice, many times from potentially top venues. They were published in not so top venues, potentially, and they went on to win the Nobel Prize afterwards. And I gave you one example from a PhD thesis of a respectable quantum physicist, as you heard earlier. So be resilient. That's why resilience is very important and related to feedback. Be resilient. You will get all sorts of feedback. There will be all sorts of folks that may actually, for whatever reason, derail you from following a particular line of research. That may not be necessarily good. So follow your passion, and do not get derailed by naysayers necessarily, unless there's something good here and you're wrong. And it's important to admit that you're wrong, of course, at times when that's really true, right? But sometimes it's very hard to say whether you're right or wrong. You do need to explore scientifically a potential theory and potential idea to see where it goes. That's why following your passion is really important. So in the end, learning and scholarship are what really matters. That's why I say quality of your work defines your impact. And I think hopefully this is exemplified by the Hugh Everett example that I showed you, that I mentioned earlier. So quality of your work is really important, and focus on quality and not quantity necessarily. But of course, if you can get both quality and quantity, that's great, right? If you have 10 ideas that are of great quality, that's better than one idea of great quality potentially, right? Assuming they're equal quality. Okay, so building infrastructure, I think, is also important. Enable your passion by building infrastructure. This is important to focus on big ideas, potentially big projects. And I think our research has benefited a lot by building infrastructures, for example, the DRAM testing infrastructure, flash memory testing infrastructure, simulation infrastructures for different types of memories, etc. And we've open sourced many of these infrastructures later on. And the infrastructure that we built for our FPGA-based analysis of bioinformatics and genomics applications, they're also open sourced, as you can see. So of course, building infrastructure, doing all of these things requires working hard. And I think there's no question about this. In the end, if you want to do something big, you have to work hard. And I do not believe that there's any shortcut. So that's why I think working hard is a good characteristic of a student. So finally, let me conclude. I think I've said a lot of things and probably took much longer than I was expected to, even though there was no time limit. So feel free to ignore any of this that I said. I will conclude with some suggestions that are basically copy and paste from some slides in the end. So if you're aspiring to do a PhD or research, or if you're aspiring to do something big, these are my personal suggestions to you. Some other people may have some other suggestions. I will say that start out with the right motivation and mindset, good mindset. Set your own bar high. Focus on continuous growth and learning, making yourself better and better at, let's say, everything. But you can, of course, set specific goals and make yourself better and raise the bar. Keep raising the bar. That's how you become better and better. Think big, aim high. I think that's another way of saying what I said in the previous slide, let's say. And follow your passion, basically. Do not get derailed by naysayers. Don't abandon some big idea that you believe in just because the world is against you. Maybe you will find something that's important, but of course, take into account good feedback. Build infrastructure to enable your passion. It's not always easy to actually show the importance of what you're doing, prove your theory, let's say. So you need to build infrastructure to do it. And that requires hard work as well. In the end, research is probably 1% idea, or maybe 0.1% idea, and 99.9% sweat to show or prove that idea. And idea, of course, evolves along the way, right? So being resilient is very important to enable this. And I think in the end, what is really important is focusing on learning and scholarship so that you can grow. And never forget that the quality of your work defines your impact. And I believe with good mindset, good goals, good focus, you can make a good impact on the world. And I believe that this is true for any undergraduate in the world. It doesn't matter what your background is, where you're from. Basically, everybody is diverse. We're all different, right? It doesn't matter who you are. As long as you have a good mindset, goals, and focus, and follow good principles, I believe anyone can make a good impact on the world. So I will finish with two quotes that I like. There are many quotes I like, but I like these two quotes in particular. I actually finished recently my digital design and computer architecture course with these two quotes as well. These are from a famous Irish playwright who won the Nobel Prize for the plays that he wrote. Well, I guess I gave who it is, so I'm going to put it over here. This is a quote that says, "The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. Therefore, all progress depends on the unreasonable man." And I like this, actually. It's good to be unreasonable, and it's good to be a critical thinker so that you can change the world. If you actually do not think critically, it's very hard to change the world, right? And I like the second quote from this person also: "Progress is impossible without change, and those who cannot change their minds cannot change anything." And I think it's really important to be open to change and feedback, and while following your passion as well. So with that, I will conclude. I hope this was useful, and I look forward to the panel where we will, and your questions in the live session. Thank you and take care.